before we get into this short little demonstration, folks, I just want to be very clear on the values that the index of the summation can take on. We start at minus k. Okay, and I won't write them all down, but we'll use skip some values. We'll hit I is equal to -1. Okay, and also 0 is going to be included. Okay, you're going from minus to positive integers, so 0 will be included. You will hit 1 as an indice, and of course, we'll terminate with k. Now, if you'll notice the way this is set up, we're saying that any odd number raised to a natural number power, okay, can be written as the sum of that odd number of integers, consecutive. All right, now that's a mouthful, but that's exactly what this says. Now, we should also say that n is any natural number. Some might think you need to do induction on this. You don't. Just basic laws of exponents get us through this. Now, perhaps the best way to get started here is just work with a concrete example. K equals 3, okay, and n equals 2. So k equals 3 would lead to 7 squared, right? If you put a 3 right here, you get 2 times 3 is 6 plus 1 is 7, so that's 7 squared. And again, if you range through these indices, just like I said up here, we start at -3 because k is equal to 3, -2, -1, okay? And then right here, just to be clear, this is 7 plus 0 right here. So that's what I mean. We are including the index of 0 in this summation. I don't think this is super common. Usually you range either through the positives or the negatives maybe. But in any event, just want to be clear on all that. And notice what happens here. Everything in sight cancels, and you have 7 times 7, right? In other words, -3 cancels, -2 cancels, -1 cancels with the 1, the 2, and the 3 over here. So we have 7 copies of 7, which is also known as 7 squared. Now, it's awful tempting, you know, to add all these up. This would be 4, what? 4 plus 5, plus 6, plus 7, plus 8, plus 9, plus 10. But you'll see that does add up to 7 squared. Okay, again, you have 7 copies of 7, all right? So that motivates this. I guess we'll call it a proof if you want to tolerate that. The more general case here where we have k is a fixed natural number and n is any natural number. This is, I could have written a little bit more, but you can see the way it's written. All this, everything cancels. Like this minus k is going to cancel with a plus k over here. This -1 will cancel with the +1 here. And notice right here again, we have 2k plus 1 quantity elevated to the n minus first power, n minus 1 power, and then plus 0. I'm just putting it there conspicuously, right? Because the k is ranging through, that's the middle term, okay? That's the middle term. That's where the oddness comes in. There's an exact middle term for a list of odd integers. You have to average the middle two if it's an even number. Okay, but in any event, we get the very same kind of result here, except albeit a little more generally. You would actually get 2k plus 1 occurrences of the quantity 2k plus 1 raised to the n minus 1 power. Now, so you see, this is not induction as much as people want to scream induction here. I've seen so many people think, oh, you see a lot of for all n, and then that means you have to have induction. But this is just laws of exponents here. So this is just equal to 2k plus 1 quantity elevated to the nth power. And notice all we did right here was b, where b is an arbitrary base, b times b raised to the n minus 1. again, it's superfluous to put the 1 here, but hopefully it adds a little bit of clarity. That's equal to b to the n, you see. So no induction is necessary here. As much as I've had people write comments and stuff, oh yeah, it's easier to do it by induction. No, it's unnecessary, plain unnecessary. See, this is a statement that holds for all n, right? All natural numbers n, or all integers really. For our purposes, it's just holding for natural numbers, but it holds for all integers and rational numbers. And so you see, you have a universal quantifier right in the middle of all this, so you don't need induction on something like this. This actually proves our result. So I'll put, I guess I can write QED here for this marginal proof. And I would have written more. I wanted to keep all this on one line. I could have showed you a few more I's here. Hopefully this is enough to have this I sitting out here. All I did was show you one occurrence of it here, one occurrence of it here. We have 0, which is I, and then 1, and then k. But all those constants, all those I's cancel out because of this symmetry. And we've proved what we set out to prove. I think it's a cool result. And let's see, that is what we were trying to prove, right? Yep. Okay, thank you for viewing.